Hey, welcome back. In our last video, we learned about the power rule, which is a great way to find the derivative of polynomial functions really quickly. However, not every function can be written as a polynomial. Trigonometric functions, exponentials, and logarithms can all be lumped together into one category called transcendental functions because they can't be written as polynomials. So how do we find the derivative of transcendental functions? Well, we need more derivative rules. So today we're going to look at the 6 trigonometric functions as well as exponential and logarithmic functions and learn how to take the derivative of those functions, and we're going to add it to our derivatives repertoire. So to start off, we've got our 6 trig functions and their derivatives. The derivative of sine x is cosine x, the derivative of cosine x is negative sine x, the derivative of tangent x is secant squared x, the derivative of cosecant x is negative cosecant x cotangent x, the derivative of secant x is secant x tangent x, and the derivative of cotangent x is negative cosecant squared x. Now you're probably wondering, where do all of these come from? Well, what I'm going to do after I post this video is post a why it works video that shows where the derivative of sine and cosine come from, and then later, a couple of topics from now, I'll be able to come back and show you where the other 4 come from. But for now, here's a trick for remembering them. Look at sine, tangent, and secant. The derivative of sine x is cosine x. The derivative of cosine is negative sine. The derivative of tangent is secant squared. The derivative of cotangent is negative cosecant squared. And the derivative of secant x is secant x times tangent x. The derivative of cosecant x is negative cosecant cotangent. So there's a little bit of a pattern there that helps you memorize these 6 trig functions pretty quickly. So all I ask is that you memorize these as quickly as you can, and let's put them right to work. Example 1, the derivative of sine x minus cosine x. Well, just like with polynomials, we're going to take our derivative piece by piece. So the derivative of sine x is cosine x minus the derivative of cosine x, which is negative sine x. Minus a negative, of course, means addition, so my derivative is cosine x plus sine x. Example 2, find the derivative of 4 tangent x plus 3x squared. Again, piece by piece. The derivative of 4 tangent x, just like with polynomials in the power rule, a coefficient is going to remain in your derivative. So the derivative of 4 tangent x is 4 secant squared x plus the derivative of 3x squared, using the power rule, is 6x. Example 3, take the derivative of sine x plus x all over 3. Right? Again, we're not equipped to handle fractions yet, so what I need to do is rewrite this in a way that's easier for me to work with. I'm going to take sine x plus x over 3 and split that into 2 fractions. And now that I've written it this way, the derivative comes naturally. The derivative of 1/3 sine x is 1/3 cosine x, plus the derivative of 1/3 x is just 1/3. That about does it for our new trig derivatives. Now we're going to shift gears and look at exponential and logarithmic functions. Again, I can't tell you where all of these come from yet because we don't know enough calculus. I can make a why it works video for e to the x, but the others will have to come later. So let's start with the derivative of a to the x. So an exponential function of any base has derivative a to the x ln a. But what if that base was e? The derivative of e to the x would be e to the x ln e. ln e is 1. So the derivative of e to the x is e to the x. So e to the x is kind of special because it's its own derivative. And the derivative of log base a, so a logarithm of any base, the derivative of log base a of x is 1 over x ln a. And again, we ask ourselves, what if this base was e? Log base e, or the natural log of x, would have a derivative of 1 over x ln e. Again, ln e is 1. So the derivative of the natural log of x is 1 over x. So just like with your 6 new trig derivatives, commit these to memory as quickly as you can, and we're going to get some practice with them right away. Example 4, find the derivative of 4 to the x minus cosine x. So piece by piece, the derivative of 4 to the x is 4 to the x ln 4 minus the derivative of cosine x is negative sine x. So minus negative sine x, I'm going to write that as plus sine x. Example 5, the derivative of 3e to the x plus log base 3 of x. So again, that 3 coefficient is just going to hang out there. So the derivative of 3e to the x is 3e to the x because it's special, plus the derivative of log base 3 of x is going to be 1 over x ln 3. And there's probably a common denominator to find there, but I'm going to guess that for most purposes, we're okay leaving our answer just like that. And last for this group, example 6, find the derivative of 5 over 2x cubed plus 4 ln x. So I'm going to rewrite this problem in a way that's nicer. I'm going to write it as 5/2 x to the negative 3 plus 4 ln x. Now that I see it like this, I can use the power rule and my new rule for natural log to take the derivative. So the derivative of 5/2 x to the negative 3, negative 3 times 5/2 would be negative 15/2 x to the negative 4, plus the derivative of 4 natural log of x is going to be 4 times 1 over x, or 4 over x. Okay, and this is a box and run answer, but we can simplify this a little bit. So make sure you know how to find a common denominator if the need should arise. Example 7, find the equation of the tangent line, boom, point and slope, to f of x equals 2 plus ln x at the point where x is e. So to find my point, I'm going to take my x value, e, and plug it into my equation. 2 plus ln e is 3. 2 plus 1 is 3. And my slope. To find my slope at this point, I'm going to need my derivative. So f prime of x is equal to 0 plus 1 over x. So f prime of e is 1 over e. Got my point, got my slope, point-slope form. So y minus 3 equals 1 over e times x minus e. Example 8, you're going to need your calculator for this one. Given f of x equals e to the 4x minus 2, evaluate f prime of x at the point where f of x crosses the x-axis. So in my classroom, we use TI Inspires. Maybe you use a TI-84, TI-89, or something else altogether. But generally speaking, the strategy for this problem is the same. We want to know where e to the 4x minus 2 crosses the x-axis, or where it equals 0. So on my calculator, I want to graph this function and find the value where it crosses the x-axis. And it happens to be at 0.173. Now, that's not an exact value. That's an approximation. And I'm about to use this value to continue working in the problem. So to make sure that I don't make any mistakes, that I don't have any rounding errors, I'm going to use my calculator to store that value. And by storing that value, I can call it back later in its exact form, not its rounded form. And that makes my final answer more precise. So I've been asked to find f prime of x at the point where f of x crosses the x-axis. So I want f prime of 0.713. Now, no matter what calculator you're using, it probably has the ability to take a function and then tell you what the derivative is at a certain point without ever having to know what the derivative actually is. So f prime of 0.173, again, don't plug in 0.173, plug in the stored value that you had earlier. If you use a stored value, if you plug in the exact value, then your answer is going to be exactly 8. So if you got a decimal value close to 8, it might be because you didn't use a stored value. So get in the habit of storing a value that you get in the middle of a problem that you need to use later on. Example 9 is a very similar problem. Given g of x equals the natural log of tangent of x squared, evaluate g prime of x at the point in the interval 1 to 2 where g of x equals 0. So I'm going to take my calculator. I'm going to graph natural log of tangent of x squared. I'm going to restrict my window so it's from 1 to 2 and find where it crosses the x-axis. Once I've found that x value, I'm going to use my calculator to plug that x value into the derivative without ever needing to know what the derivative even was. So using my calculator, I found that the graph crosses the x-axis at 1.982, and then I have my calculator evaluate the derivative at 1.982. Again, I stored the exact value and then plugged it in, and I got 7.923. So remember, in calculus, 3 decimal places is the default. So give me all your answers to 3 decimal places, 7.923. All right, 2008, BC number 4. For values of h very close to 0, which of the following functions best approximates f of x equals tangent x plus h minus tangent x over h? Well, when they say for values of h very close to 0, they're kind of talking about a limit. And when you see this, hopefully you recognize that as the limit definition of derivative. So I've got f of x plus h minus f of x over h. So this is all just a big way of saying what's the derivative of tangent x. We learned that one today. The derivative of tangent x is secant squared x, so my answer is E. 2012 AB number 4, if f of x equals 7x minus 3 plus ln x, then f prime of 1 equals what? Well, two-step problem. Step 1, find the derivative. Step 2, plug in 1. So f prime of x is going to be 7 minus 0 plus 1 over x. So f prime of 1 is going to be 7 plus 1 is 8. So my answer is E. 2012 AB number 18, limit as h approaches 0 of the natural log of 4 plus h minus the natural log of 4 over h. So I see this limit as h approaches 0, so I'm immediately thinking about the limit definition of derivative. So is this f of x plus h minus f of x over h? Kind of. And the reason why I say kind of is because the function here, f of x, would be ln x, but we've already plugged in a 4 into ln x. So this is f of 4 plus h minus f of 4 over h. So if f of x equals ln x, this limit is saying what is f prime of 4? Well, the derivative of natural log x is 1 over x, so f prime of 4 is 1/4. So my answer is B. 2012 AB number 78. Okay, I want you to notice since the question number is 76 or higher, this means this was a calculator active problem on the AP exam. Very quickly you'll realize you need your calculator for this anyway, but the question number gives it away. The graph of y equals e to the tangent x minus 2 crosses the x-axis at one point in the interval 0 to 1. What's the slope of the graph at this point? So really similar to the two questions we had up in the notes. I need to graph it, I need to find the point where it crosses the axis, I need to store that value, and then I need my calculator to evaluate the derivative at that stored value. So when I graph e to the tangent x minus 2 and restrict my window to be 0 to 1, I see that it crosses the x-axis at x equals 0.606. I stored that value, and then the way you read this is y prime evaluated at, the vertical bar means evaluated at x equals 0.606. Again, I plugged in my stored value right there and got 2.961. So my answer is D. And last one for today, 2012 BC number 77, another calculator problem. Let f and g be functions given by f of x is e to the x, g of x is x to the fourth. On what intervals is the rate of change of f of x greater than the rate of change of g of x? Well, when they talk about rate of change, they're talking about derivatives. So I want to know, when is f prime of x greater than g prime of x? Well, I can find these two derivatives. F prime of x, the derivative of e to the x is e to the x. And g prime of x, the derivative of x to the fourth is 4x cubed. So you might be tempted to graph both of these separately and then look at the graph and see when one is higher than the other. Unfortunately, because the graphs are so close together, sometimes it's kind of hard to tell. So better than drawing these two graphs separately, why don't we graph e to the x minus 4x cubed and see when that is greater than 0. So when I look at the graph of e to the x minus 4x cubed, I see that the graph is positive until it gets to the x value 0.831, negative for a while, and then positive again from 7.384, on and on and on. So that means that e to the x is bigger than 4x cubed from negative infinity to 0.831, and from 7.384 to infinity, which is what answer choice B says. All right, so to recap, today we learned 10 new derivative rules. The derivative of sine, cosine, tangent, cosecant, secant, cotangent, and a to the x, e to the x, log base a of x, and the natural log of x. And so, using those 10 new derivative rules in combination with the power rule, we can answer all kinds of new derivative problems. Hope that helps. Thanks for watching.